Hello and welcome back, everyone. Moving on to the last section in chapter 4. So it's going to be the last day that we're really diving really deep into differential forms and the exterior derivative. Today we're really talking about a concept known as primitives. And then there's a very closely related concept to primitives that we'll use in the context of primitives. These are called closed and exact forms. Of course, closed and exact referring to differential forms. There's a special class of differential forms that are going to be called closed or exact. And what's the motivation here? The motivation is that we have been introducing differential forms as infinitesimals of area or volume, etc., as well as our differentials dx, dy, dz appearing in integrals. We're trying to set up a definition for integration in higher dimensions. And in particular, we're trying to set up an integration in the context of a fundamental theorem of calculus. We did start out this entire text with a naive fundamental theorem of multivariable calculus, and then I teased the true fundamental theorem, which was the generalized Stokes theorem. We're getting really close to actually being able to understand what the generalized Stokes theorem is saying, now that we know what differential forms are. But to get there, we're going to have to figure out, regular fundamental theorem of calculus relies heavily on the integral as an antiderivative. That's really what at least this second fundamental theorem of calculus is saying, that the integral is an antiderivative. The first says that the derivative, I suppose, is an anti-integral. You can think about it that way as well. But the integral is an antiderivative. We ask the question, is there such an object as a multidimensional antiderivative? Right? Can we get some sort of similar notion in multiple dimensions? Well, we did discover the derivative of a multidimensional function as the total derivative. And in that setting, there is always an antiderivative. But in a lot of cases, we don't actually have total derivatives sitting around, especially when we're integrating, right? Because I'm going to point our attention back to these differentials. These differentials are differential forms, are what we actually integrate against. And so in the context of differential forms, we're no longer thinking about df as the total derivative, but rather now df as the exterior derivative. And when we think about df as the exterior derivative, it won't be possible to always find an antiderivative. So that's a little bit sad. A little bit sad in the way that, the way it feels like we should define integration, which is the way we want to define integration with these differential forms, that we won't actually be able to find an antiderivative. Not necessarily, at least. And so that's why I say here, the comprehensive answer to our question is no. There are specific cases where the answer is yes. So what are we going to do today? We're going to figure out just what multidimensional antiderivatives are and how we can differentiate those cases of no versus yes. There's going to be a pretty easy computation we can take that'll tell us whether or not it's available to produce this multidimensional antiderivative. So in the context of what I'm going to call anti-exterior derivatives, right? Anti-exterior derivatives, since we're computing the exterior derivative lately, we call these specific anti-exterior derivatives primitives. Okay, so a primitive or a primitive differential form just happens to be, right, if I start with, here's my lowercase f, I'm going to have lowercase f be a k form. A primitive of that k form is going to be a capital F. Itself will be a k minus 1 form, with the property that if I take the exterior derivative of capital F, I recover lowercase f. So really straightforward. If I take the exterior derivative of capital F, I recover lowercase f. Nothing more complicated than that. Let's look at some examples of these primitives. So I've got a lovely 3 form here. So here's a 3 form f, and my 3 form f is defined to be constantly 3 everywhere, of course, because it's a 3 form dx dy dz, or dx wedge dy wedge dz. Turns out you can find a primitive. I'm just going to propose it, and then we're going to verify that it is a primitive. So let's propose a capital F, a differential 2 form, very important. It's got one lower number of forms in it than the original. And this capital F I'm proposing will be z dx wedge dy plus x dy wedge dz plus y dz wedge dx. Now, why is this going to be a primitive? Let's just go ahead and compute an exterior derivative. How does this get computed? Well, we're just going to apply our capital D to both sides, and of course it can just distribute onto the coefficients. D on z will just give me no surprise dz, d on x will give me no surprise dx, d on y will give me no surprise dy. We shouldn't forget we pay the price of wedges after each of those d's. And then if I rearrange each of those wedge products, remember I can rearrange wedge products up to including the correct number of pluses or minuses, it turns out all of these stay as positive 1, and so we can add them all together and just get 3 dx dy dz, which of course is our original differential form we were searching for, this original f. And so we verify something's a primitive. Let's get another example of a primitive. So here I've got the differential 3 form g of x, y, z equals 3 times dx wedge dy wedge dz. This is actually the same differential form as earlier. I give it a new name. So I give it the new name g. Not a big deal. I propose that there is a different primitive here, this capital G. I guess this one should have been a capital G here. So I claim this other primitive, capital G, as 2z plus x dx wedge dy, 2y minus x dy wedge dz, and 2y plus z dz wedge dx. And if I compute the exterior derivative on this capital G, I'm going to apply it to each of the coefficients individually and pay the price of a wedge. And of course, when I do, I'm going to get something like 2 dz plus dx. I'm going to get 2 dy minus dx, and I'm going to get 2 dy plus dz. And then I'll go ahead and distribute these wedge forms to each of their terms. And distribute. And then I'll do my fancy rearranging, or equivalently noticing here's a dx wedge dx, so that's 0. Here's a dy wedge dy, so that's 0. Here's a dz wedge dz, so that's 0. Everything else is going to get some rearranging to a dx dy dz, dx dy dz, dx dy dz. And what do we end up with? Well, we end up with a 2 minus 1 plus 2. So that's going to be 2 minus 1 is 1 plus 2 is 3 copies of dx wedge dy wedge dz. I've got one more example where we can find a primitive. Here's the differential 3 form h. H of x, y, and z is 3. dx wedge dy wedge dz. Same form as before. And now I'm going to purport that there is yet another primitive here. I'm claiming capital H, defined by 3z, dx wedge dy, is also a primitive. Let's see why. Let's compute the exterior derivative on h. I can pass it directly to the coefficient at the price of a wedge. That's going to give me 3 dz, and then I'm going to rearrange dx of dy dz and get exactly 3 dx wedge dy wedge dz. So what we've encountered here is 3 cases of the exact same differential form at the beginning, but 3 different primitives. That was the first primitive I claimed. This is the second primitive I claimed, considerably different. Here's the third primitive I claimed, also different. So I've got this remark here. Primitives are not unique, in a manner much worse than ordinary antiderivatives. If you look at those 3 previous examples, I had 3 primitives that were really substantially different. There's the one, there's the second, there's the third. They were differing by much more than just the constant plus c, right? Regular antiderivative of f would be capital F of x plus c. That's all we had to do in Calculus 1. With the plus c, now we've got something much more intense than plus c. It turns out it's really hard to figure out just how many other functions can be involved in primitives. And so we're not really going to discuss how to include our version of the plus c in higher dimensional integrations. It'll turn out not to be super important, but what is important is that you realize primitives are very, very not unique. You're going to get all sorts of superfluous primitives in many cases. So hopefully we can come up with a nicer, more direct way to compute primitives than rather have to search through infinitely many possibilities. We're also going to analyze a case in which a differential form doesn't have a primitive, because if we go back to the beginning, what did I claim? Primitives can exist. This property can be true, but it certainly doesn't have to be true. I said the comprehensive answer to multidimensional antiderivatives is no, they don't exist. So let's look at a case where primitives maybe cannot exist. And actually, I'm going to give a case where primitive does exist, but also a primitive doesn't. So let's look at the form, differential form, one form in 2 dimensions, y dx plus x dy. I can go ahead and compute the exterior derivative of what I claim to be a primitive. Claim as primitive. I'm going to compute the exterior derivative of that f. So that's going to be a d on x times y. I just get to use the product rule if I want to. That's what dx times y plus x times dy. And what do you know? That's exactly what my differential one form wanted to be. Okay, so there is a primitive to y dx plus x dy. Now I'm just going to modify this function just very ever so slightly. So this differential form, let's modify it. Let's modify the coefficient on y. Up top, I've got a coefficient of 1. On the bottom, I'm going to modify that coefficient to 0.999. So close to 1, but not quite 1. And I'm going to claim that this differential form has no primitive. And how can I prove that it has no primitive? Well, I'm going to assume, let's assume a primitive exists and study its properties. So what would the properties of the primitive of this differential form be? Well, I know if I compute the exterior derivative of a primitive, then it'll have to agree, right? The partial x of that primitive will have to agree with 0.99y, and partial y of that primitive will have to agree with x. Those will have to be true. That's what I've written down here. Okay, so that primitive has a property that if I take partial x on the primitive, I get 0.999y. If I take partial y on the primitive, I get x. But Schwarz's lemma comes around and it says, hey, let's go ahead and compute partial y on both sides here. And let's compute partial x on both sides here. It's not too hard to compute these. On the left-hand side, I'm getting 0.999, and on the right-hand side, I'm getting 1. But Schwarz's lemma is telling me, hey, that's partial y, partial x, and on a function that needs to be the same as partial x, partial y, these need to be the same. They must be equal. Otherwise, it's not a function. And we look at that, 0.99, definitely not equal to 1. So this function can't exist. The function that we would love to be a primitive here can't exist. The moment I change that coefficient on y, right, it was such a subtle change between the coefficient on y, and yet the subtle change prevents any primitive from actually existing. So this is why it's subtle when you can tell if a primitive does or does not exist. Thankfully, Poincaré turned around and he told us there's a really easy way to tell if a primitive can exist before we attempt to find one. This is actually part 2 of his lemma. Let's recall what part 1 was before. Part 1 said d squared of any differential form is constantly 0. That was part 1. Part 2 says we're going to give some names. We're going to give some names to differential forms whose exterior derivatives are 0. We're going to call all differential forms whose exterior derivative is 0. We're going to give them a name, closed. So those differential forms have the name closed. We're also going to give a name to differential forms which have primitives. We're going to call all differential forms with existent primitives. We're going to call all of those exact. There's an exercise at the end of this chapter on why we use the word exact here. And in fact, closed will make a little bit more sense in the future chapter when we cover the generalized Stokes theorem. We're going to call all differential forms with existent primitives exact. Poincaré turned around and said, as long as you have a finite dimensional contractible domain, don't worry about what that means. Most of the things that we encounter are going to be finite dimensional contractible domains. Poincaré turned around and said, hey, these are the same thing. All closed forms are exact, all exact forms are closed. So it means that these imply each other. So I'll say implies. So if I take an exterior derivative of a form and I get 0, then I know that a primitive exists. And if I know a primitive exists, then I know the exterior derivative of that form is 0. And in fact, this upwards direction is actually part 1 of Poincaré's lemma. Because if a primitive exists, then my form is equal to the derivative of another form. But that means if I take the first derivative of my left-hand form, it's the second derivative of my right-hand form. The second derivative of any form happens to be 0. So really, the special part about Poincaré's lemma is this downward arrow. We can test whether or not a primitive exists by checking if the exterior derivative is equal to 0. That's what we should take away. We can test if a primitive exists by checking if an exterior derivative is equal to 0. So how could we test one of these? I had the proof there. It was actually quite intense. If you want to pause, you can check the proof out or find the text. Let's actually look at a case where we're going to test if a primitive exists. So big question, does a primitive exist? Does a primitive of this form exist? We're going to check by seeing if the exterior derivative equals 0. So let's go ahead and compute an exterior derivative here. I can just distribute it onto the coefficients at the cost of a wedge, right? So they're distributed on my first coefficient, wedge dx, distributed on my second coefficient, wedge dy. What's going to be that x derivative dx squared is going to be 2x dx, and then x derivative y squared will be 2y dy. X derivative x squared will be 2x dx, and negative y squared will be negative 2y dy. Of course, when I distribute these wedges to each interior term, my event of a dy wedge dy will cancel, and my event of dx wedge dx will cancel. I'm just going to be left with 2y dy dx on the left and 2x dx dy on the right. But of course, there's a dy dx, there's a dx dy. And if I go ahead and exchange the order at the cost of a minus sign, I'll put a minus sign here, we get 2x minus 2y dx wedge dy, and that's the most simplified. Most simplified, but importantly, not equal to 0. Why is it important it's not equal to 0? Therefore, no primitive can exist. This is what Poincaré's lemma is useful for. No primitive can exist because my exterior derivative of the form in question was not equal to 0. Let's look at another case. Here's a slightly modified differential form. You ask the same question, does a primitive exist? Yes, if the exterior derivative equals 0. No, otherwise. Well, let's compute an exterior derivative and find out. There's my exterior derivative. I'm going to distribute to both coefficients at the cost of a wedge. So I've got d against the first coefficient, x squared plus 2xy, wedge dx. I have d against the second coefficient, x squared minus y squared, wedge dy. And then I'm going to compute the exterior derivative on each of the coefficients. The derivative of x squared will give me 2x dx. Derivative of 2xy, there's going to be a product rule there, so 2y dx plus 2x dy. If I take the derivative of x squared minus y squared, derivative of x squared is 2x dx, and on negative y squared is negative 2y dy. Then I'm going to go ahead and distribute my wedge products to each of the terms out front. And when I do that, as before, if I have a dx wedge dx, those disappear, dx wedge dx disappear, dy wedge dy disappear, so I'm just left with 2x dy wedge dx and 2x dx wedge dy. But of course, at this stage, if I have 2x dy dx, 2x dx dy, I can exchange the order at the cost of a minus sign. We're going to get negative 2x plus 2x, or in other words, we're going to get exactly 0 copies of dx wedge dy. In other words, we're getting a big 0 there. So this says, yes, a primitive does exist. That's what Poincaré's lemma can do for us. It'll tell us now it's not fruitless to attempt a search for a primitive. So you may be interested now in actually finding the primitive. It's a fairly complicated thing to do. If you look at the proof of Poincaré's lemma, we do describe kind of how to do this in all of generality. There's something called a fiber integral, or a fiber integration that you perform on a modified version of your original differential form. That fiber integration will produce a primitive for you. If you define your capital F as this fiber integral that we just include in the lemma, it turns out that that specific capital F will be a primitive, specifically in the case when the lowercase f is a closed differential form. However, we're not really going to be going through finding primitives using that fiber integration, even though technically that's what's happening in this proposition. We're just going to find some primitives of exact, equivalently closed, one forms. So we're just going to restrict ourselves to one forms for now. So restrict primitive calculations to being 0 forms of one forms. All right, the primitive of a one form would be a 0 form. How do we compute these? It's actually pretty straightforward. So if we start with our one form, lowercase f, and let's assume it's exact, meaning d lowercase f equals 0, thanks to Poincaré. So as long as that's going to be true, then what can we do? Well, we need to consider f actually as a standard n-dimensional vector. All right, so normally f, if I have maybe x, y, z, this would be like f1 dx plus f2 dy plus f3 dz, right? Different coefficient functions, f1, f2, f3. Just consider them now into a vector, f1, f2, f3. Once you place them into that vector, you take the dot product of that vector with just x, or your vector of variables. This is a vector of variables. And you evaluate the argument of the function. Argument of differential form is now t times the vector of variables. So in other words, each variable gets a coefficient of t by it, and then you're integrating in that variable t. So the t is what gets integrated. We haven't discussed multidimensional integration very much, so this is useful that it's a one-dimensional integral, right? It's just calculus 1 integration once you actually perform the dot product. So we're going to see what that looks like in examples. It's actually a fairly easy proof on why this is the case. It just reduces to the fundamental theorem of calculus in one dimension. So here's 0 to 1 partial t dt. Of course, this is just the integral of a derivative in that variable. So you just take the antiderivative, which means get rid of the partial t, take the antiderivative, evaluate on the lower bound and the upper bound. And of course, that's just going to be, capital F at x minus capital F at 0. But you make the assumption from the beginning that capital F at 0 is just equal to 0. And so fairly easy proof for that problem. What's a little more complicated is actually computing these primitives. So let's go through some examples of computing these primitives. All right, so what I have here is a one form, which I would like to compute a primitive of. So here's the one form I'm going to compute the primitive of. Remember to actually use this formula, 0 to 1 f of tx dot x dt. To use it, we have to reinterpret our differential form as a vector. So I'm going to reinterpret this form as a vector. The coefficient on x is just going to go in first, x squared plus 2xy, and then the coefficient on y, we have x squared minus y squared. So there's my vector. You can see that's what I have here. And then I have to go through a little extra work. Not only is it the vector version of that differential form, but it's evaluated on t times my variables. So rather than a variable, I need to replace each of these variables with t times the variable. So replace each variable with t times the variable. That's what I have down here. So instead of x squared, I have tx squared. Instead of x, I have tx. Instead of y, I have ty. Instead of x, I have tx. And instead of y, I have ty. So I've just replaced every variable with t times the variable. And finally, I do have this remaining x, which is the vector of variables. So vector of variables. And be very careful here. There's no t in that vector of variables. So just an x and just a y here. Okay, so from this point onwards, that's just going to feel like, after a dot product, regular calculus 1. Okay, maybe calculus 1 with a couple of variables sitting around, x's and y's sitting around, but you're just integrating in the variable t here. Right? So you're just going to find all of these t's after your dot product and integrate them individually. So let's perform that dot product. We're just reading straight across. We're going to take this entire term, multiply by x, that's this, and then we're going to take this entire term, multiply by y, that's this. Then, because it's a dot product, we add all the terms together. Now we simplify. What do I actually have here? It looks like I've got x, tx squared, so that's tx cubed. I've got y, ty squared, so that's t squared y cubed. I've got 2tx ty and an x. And I've got tx squared and a y. All of those together are going to give me 3t squared x squared y. So that's me combining all of my terms together. Now I'm just integrating in the variable t. So I'm just finding the antiderivative of that t squared, and that t squared. Obviously the antiderivative is t cubed over 3. T cubed over 3 in the middle as well, but there was already a 3 to cancel with it, and t cubed over 3 again. Of course, in the variable t, I've got my lower bound and my upper bound. That's saying I'm going to evaluate on the upper bound of t equals 1 minus lower bound of t equals 0. So I just plug in the upper bound. That's when t equals 1. So a 1, a 1, and a 1. And then I subtract the lower bound when t is 0. So 0, 0, 0. Turns out the 1s are the only terms which survive. And I get x cubed over 3 plus x squared y minus y cubed over 3. This is what I'm claiming is the primitive. Right? If my proposition were true, what I just came up with should be the primitive of this differential form. Let's verify that that is actually the primitive of the differential form. So we're just going to take an exterior derivative of this, cross our fingers. So we'll go d on this whole term. Of course, that's distributing to each term individually. When I take d of x cubed over 3, that's going to give me what? X squared dx. When I take d on x squared y, that's going to give me a product rule. So I'm going to have 2xy dx, that's my derivative in the x variable, plus I'm going to have x squared dy, that's my derivative in the y variable. And then on my negative x cubed over 3, I'm going to end up with minus y squared dy. That's going to be my exterior derivative. And of course, what do I actually have here? I have two terms with the x, those can be combined, two terms with y, those can be combined, so I'll have x squared plus 2xy dx, and I'll have x squared minus y squared dy. That is precisely the differential form we were looking for at the beginning. So yes, I have indeed found a primitive. Let's get one more example of a primitive computation of a one form. Just a little bit more complicated here. I've added a dimension. We've got dx, dy, and dz. And as before, if we're going to use this lovely formula, which is the integral from 0 to 1, f of t times my vector of variables, dot product of the vector variables dt, then I'm going to need my differential form phrased as a vector rather than directly as a differential form. So let's write our form out as a vector. We're going to take the x component and include it in the x component. We're going to take the y component and include it in the y component. We're going to take the z component and include it in the z component. So we've transitioned our differential one form into a vector. And then we do need to replace each variable in the differential form vector with t times the variable. So instead of a y sine of xy, I now have ty sine of tx ty. And instead of x sine of xy, I have tx sine tx ty. Instead of z cosine y z, I have tz cosine ty tz. And instead of y cosine y z, I have ty cosine ty tz. So I replace all of my variables with t times the variable. That's just in the differential form vector. My other vector, which is just the regular vector of regular variables, has no t on it. No t's inside. Okay, so just on the differential form vector, we include t's for each variable. Now I'm going to perform my dot product. When I perform my dot product, I'm reading straight across. First entry against x, there it is. Second entry against y, there it is. Third entry against z, there it is. And I add all of those entries together because it's a dot product. There's me adding all the entries together. And what am I actually left with when this is done? I need to simplify. I'm going to simplify from here. So if I simplify, I'm going to pay attention to some of the terms that are showing up. It looks like I've got something like tyz, tyz, both on cosine ty tz. And I also have txy, txy on negative sine tx ty. So I can simplify a little bit. When I simplify a little bit, I'm getting negative 2 txy sine t squared xy, positive 2 tyz cosine t squared yz. Wow, why is that really good the way things worked out? Let's run a u substitution with u equals t squared xy. That makes du equal, well, we're only integrating in the dt variable, right? So I'm only thinking about du. X and y are going to be considered constants here, so I'm just doing the derivative in the t variable. That's 2t xy dt. Lo and behold, that's exactly what I have out front, 2t xy. Same idea is happening over here with t squared yz. If I also run, I guess, a modified u substitution, now u will be t squared yz, so then du is 2t yz, 2t yz, there's my du. So what we end up having is two individual cases of integrating this with u substitution, integrating that with u substitution, and basically those coefficient terms are going to fall out. We're just looking for the antiderivative of sine, or negative sine, I suppose, which is positive cosine. The antiderivative of cosine is positive sine. And then the arguments for each of those stay the same. Now I have the t variable on my bounds 0 and 1. So my t variable on my bounds 0 and 1, I'm going to plug a 1 in for t, so a 1 and a 1. And then I'm going to subtract, plugging a 0 in for t, a 0 and a 0. And what do I get when that's all said and done? I get cosine of xy plus sine of yz minus 1. This is what I claim is a primitive of original differential form. So my original differential form, all the way up here, I claim I've just computed a primitive of this form. Let's check and see if my primitive is in fact a primitive. We're just going to compute the exterior derivative here. So d on this, well, d on the 1, the minus 1, I guess, will give me a 0, so I'm not worried about that. On cosine, I'll have a partial x term. That's going to give me negative sine xy, but I'll have a chain rule come through and give me a y out of that. So y sine xy, that was my derivative in the x variable. Now my derivative in the y variable on cosine xy will give me negative sine xy, but I'm going to pick up an x from the chain rule with my derivative in the y variable. And if I take a derivative of sine of yz, derivative of sine is, of course, cosine of yz. If I'm doing the partial y version, the chain rule is going to give me a z, and then a partial in the y direction, my derivative in the y direction. I'm going to add the derivative of sine of yz, again, cosine of yz, but if I'm doing the partial in the z direction, chain rule gives me a coefficient of y out front, and this was the derivative in the z direction. I will, of course, because I've got dy here, I can combine these coefficients together, and what we see is on the x terms, negative y sine xy dx, which is what I wanted. On the y terms, negative x sine xy plus z cosine yz, which is exactly what we wanted. And on the z terms, a positive y cosine yz, which is just what we wanted. So we have indeed found a primitive of our differential one form. I'm going to do one more example, more as a caveat than anything else. This is an example of a non-primitive computation. Let's start with the differential one form here. And let's go ahead and run the procedure to compute a primitive. So here's my procedure yet again to compute a primitive. So I'm going to have to replace my differential form with its vector version, the x component, of course, being x squared plus y squared, and the y component x squared minus y squared. Then I replace every variable with a multiplication by t, so tx squared, ty squared, tx squared, and ty squared. And I take the dot product with the regular vector of variables, and I perform my integral. If I take that dot product, that's just going to be tx squared plus ty squared times x, plus tx squared minus ty squared times y. And now I'm going to simplify as always. When I simplify, it looks like I'll have a single copy of tx cubed, I'll have a copy of tx squared y, I'll have a copy of tx y squared, and I'll have a copy of negative ty cubed. At this point, I'm just integrating in the variable t alone, so that'll be a t cubed over 3, t cubed over 3, t cubed over 3, and t cubed over 3. And I'm evaluating the lower bound 0 and upper bound of 1 for the variable t. So I'm going to plug in a 1 for each t, and then I'm going to subtract, plugging in a 0 for each t. When I do that, I do recover the following quote-unquote primitive. Okay, so I could simplify and pull 1/3 out of everything because it was there. This is a quote-unquote primitive, but let's check if it really is. By computing an exterior derivative. So if we compute an exterior derivative here, well, it's going to distribute to x cubed, x squared y, xy squared, y cubed. Exterior derivative of 1/3 x cubed is going to give me x squared. And then I'm going to have a product rule on the x squared y term. I'm going to have another product rule on the xy squared term. And then the exterior derivative on negative 1/3 y cubed will give me negative y squared. So some of my product rule terms are showing up here. That's not really what's important here. What is important is that we've taken an exterior derivative on what we claimed was a primitive. And if we look at that exterior derivative, that is definitely not the differential form we started with. The differential form we started with had a lot fewer terms in it, just x squareds and y squareds in our original one. And so somehow we performed our process and we didn't find a primitive. Why didn't the process work? Well, we didn't really check that our original differential form actually had a primitive at the beginning. So here's that differential form, the original one. Let's check if a primitive even exists. So does a primitive even exist? Well, you need to check using Poincaré's lemma, right? You take the exterior derivative of everything. So I'm going to take an exterior derivative of everything here. And of course, that just distributes to my two coefficients at the cost of a wedge. So here's my exterior derivative on the first coefficient at the cost of a wedge, the exterior derivative on my second coefficient at the cost of a wedge. And as always, dx wedge dx will disappear, dy wedge dy will disappear. So those terms are gone, and we're left with 2y dy dx, 2x dx dy. If I combine those by flipping the first one around, I'm going to get 2x minus 2y dx wedge dy. This is not equal to 0, right? Not equal to 0, so no primitive exists. Which means that, that integral I went through, this integral process, obviously it wasn't going to compute a primitive for me if a primitive didn't exist anyway. What was the point? Sometimes there is no point if you're actually looking for a primitive and one doesn't exist. However, I do have one remark that says sometimes there is a point to still attempting a primitive computation even though a primitive doesn't exist. So what we can do with any differential form here. So there's a differential form. Let's just say with a differential one form. So with the differential one form, what we can do here is this is the process that computes a primitive if it exists. That's what I'll say, a primitive if it exists. Okay, and then what have I done here is I've taken the exterior derivative of whatever my computation was. A primitive if it exists, the exterior derivative of the primitive will just give me the differential form itself. So this term should give me the differential form itself if a primitive exists. Gives f back if f is exact. Now, in the event that f isn't exact, we kind of have a remainder term. So what I've just called this is I've just taken the original differential form and I've subtracted off what was on the left-hand side. This is just original f minus the exact part. The exact part meaning everything I just computed over there. This is a very particular decomposition of one forms. This is called the Helmholtz decomposition. Most of the time that only applies in 2 and 3 dimensions, that people will call it a Helmholtz decomposition. But what we've done here is by kind of attempting to find the exact form of a differential form, the exact side of everything, we've actually extracted it off. Right? We've kind of pulled off every piece of my differential form that is exact, and then I've got everything else here. Now it turns out everything else here, there's lots of ways of describing what these are. I'm calling this everything else pre-closed. In some sense, it's like the part of the differential form which will remain after an exterior derivative is taken. Right, so that's what I'll say. The piece that remains is under one more exterior derivative. So if you took one exterior derivative of f, this, of course, this exact part would fall apart because Poincaré's lemma tells us that, and so you would just end up actually having the exterior derivative of the second half. So that's really what this decomposition does for us, but specifically in 3 dimensions, and really kind of in 2 dimensions as well, you can interpret the decompositions as an irrotational term. The exact term is irrotational. You can think about it as a divergence-free term. It turns out this pre-closed term ends up being divergence-free. Why is that important? Well, if you take the curl of your vector field, you just pick up the curl of the divergence-free term. So the irrotational term falls out. That's why we call it irrotational. It has a 0 curl. And then likewise, if we decide to take the divergence of our vector field, the divergence-free term similarly falls out, and you just get the divergence of the irrotational term. This makes a lot more sense if you look at what actually happens. So I've actually done this with our very last example. This was exactly the case from the last example. Decomposition from very last example. And I've gone ahead and plotted each of these as vector fields. So on the left here, we've got the original vector field, which has both rotational and translational motion. So they're kind of combined in the original vector field. And then what I have in the center is only translational motion. And on the right, I have only rotational motion. Now, this is actually important in physics. Sometimes you may only care about the translational behavior of a physical system. For example, you know, in the unfortunate event of like the Chernobyl nuclear disaster and a bunch of nuclear debris got thrown up into the atmosphere, I don't really care if the nuclear particles are spinning. What I care about is where they get moved. And so the translational terms tell me how actual things are getting moved through a fluid. And I don't really care how much they're spinning. But the other half of the time, I might only care about rotational motion. Why do I only care about rotational motion the other half of the time? Maybe I'm really trying to home in on the turbulent behavior that's happening around airplane wings, right? So the turbulence is not purely rotational, but it's mostly rotational. And so by decomposing my vector fields, I can kind of home in on the physical portions of the vector field that I actually care about in different situations. So this is a very cool thing that you can do with vector fields. You can do it with technically any differential form. It's usually called the Hodge decomposition when you work with other forms, and the Helmholtz decomposition when you work with vector fields. But it is a very useful thing for physicists and maybe meteorologists as well. I'm going to stop there. That finishes the chapter. We're going to actually start talking about real multidimensional integration in the next video. I'll see you then. Bye.